Hello everyone, my name is Lu Ma. I'm the beamline scientist working at a quick X-ray absorption and scattering beamline at National Synchrotron NSLS-II. So I will talk about how synchrotron X-rays help unlocking the fast charging batteries. So first, let's see. Everybody knows that we need batteries for our portable electronic devices like a phone and laptops and our watches and also for our electrical vehicles. And we all like fast charging. We don't like slow charging. I believe sometimes you may meet the same situation as me, just waiting for the phone to charging like about 20%, so it won't give me the low charging warning. And same thing for our cars. So for the traditional gasoline cars, it only takes us a few minutes to fill the entire tank. But for the electrical cars, even for the supercharger, it takes about 1 hour to charge the car to the full capacity. And with the family-based charger, it can take 6 to 10 hours for charging. It's just too slow. And why we cannot charge the battery faster? So let's go back to see what is a battery. So I'm using the lithium-ion battery as an example. So for a battery, it normally contains 3 parts. An anode usually made of graphite, like our pencil lead, and cathode, often a layered metal oxide, to let the lithium go inside, and also electrolyte, which allow the lithium ions to move between the anode and the cathode. So this graph looks like really complicated. We can take it very easy. As we can think about a ball throwing game. So during the discharge, that's when we use our battery. It seems like the anode is throwing the lithium ion to the cathode side. And on the other hand, during the charging process, that's cathode throwing the lithium ion ball to the anode. And knowing that, let's going back to why we cannot charge it faster. So for the battery charging is slow and as quick. Quick means that we are throwing more lithium ion at the same time from the cathode to the anode side. And that was too much. So the anode couldn't accept that many lithium ion. And we have a scientific definition for this process. We call it lithium plating. That means too much lithium going from the cathode side to the anode side, and they actually growing on the graphite anode side and make a metal plating process. And why it's not good? It's because when it's growing and growing, and those lithium are died, we cannot use it in the battery process. More and more, when they are growing like a dendrite structure, that's actually penetrated from the anode side to the cathode side, and that will cause the short circuit of our battery. So how can we improve the process? Something here looks very easy. That means that we need to create more channels for the lithium ion to be incorporated in the anode side. And here it's just like a cartoon to mimic the process. The actual side is much smaller than that. We actually cut the graphite to 2, so that means we create more channel for the lithium ions from the side and from the normal directions. So we have more channels for the lithium ion to be incorporated to the anode side. That looks like the anode now have a super arm to accept all those lithium ions. Alright, so how is the performance for this battery? So actually, our National Synchrotron NSLS-II can help to figure out this part. So at my beamline, I'm doing both X-ray absorption spectroscopy and also powder diffraction. So from the powder diffraction, I'm showing here the data. We can distinguish the bad spot versus the good spot. Bad spot means that we have that lithium there, and we can see clearly a peak there, and it's circled by the red rectangle here. And good spot means we don't have any dead lithium, and we can see that there's nothing there. And by the way, that's the real data we are taking with a fast charging battery for 15 minutes, which can charge to the full capacity. So during this charge process, we can see that lithium will always be there. It won't be disappeared. with more from the spectroscopy side, we can understand the charging process. So from the right top figure, that's some standard material that we took for the X-ray absorption spectroscopy. From the lower energy on the left side with the red curve to the blue curve on the right side with higher energy. That means an oxidation state happened. Higher energy means more oxidized, and lower energy to the left side means less oxidized. So during the battery charging process, we can see from the left side with the normal one-layer graphite anode. It's just a very small change, just a little. And on the right side, we actually have much more than that. That means actually our battery, the redox, is more than the left one. That means we have a higher capacity after the cycling. And more than that, so at my beamline, we can also do a mapping of the whole battery. Here we show the real batteries, the pouch cell, on the top figure. So we do the mapping point by point and focusing on the lithium peak I'm showing on the previous slides. So left side as the one-layer traditional battery, and we can see that. So it's more intense, means more dead lithium there. On the left figure, it's very obvious. On the right top corner, the dead lithium is growing and growing. So the battery capacity is dropping and dropping. While on the right side, with our development with the two layers anode structure, as almost there's no dead lithium here. That's how the battery can be fast charged. Alright, so those batteries are made by the X-Cell Center at Argonne National Lab. And I have a summary that with our tools at National Synchron NSLS-II, we can identify the live lithium versus the dead lithium. And that's during an in situ fast charging process and can be directly correlated with the battery capacity. And with this point, we are helping to optimize the material and to avoid the lithium plating to make fast charging batteries. Finally, I would like to thank my collaborator, Dr. Tianyi Li, who is a beamline scientist at Advanced Photon Cells working at Argonne National Lab, and also all the people working at my beamline, including the beamline staff, and all the support we get from our DSSI, designs and technical support, and the whole program. Thank you, everybody.